Another application of second order differential equations is series circuits. Again, we're going to just keep this pretty simple, just like we did undamped spring motion. We are only going to be looking at what's called underdamped, series circuits. But basically how this works is how your setup is here. So you have your inductor, your current goes through it. There's a voltage drop across that. You have your resistor here, again, going through it, voltage drop across that. And then you have a capacitor, voltage actually has like an inverse relationship in the drop, okay? And so I of t is going to denote that current that is going through at any certain time. The voltage drops across the inductor, the resistor, and the capacitor. And based on Kirchhoff's, I believe is how you say that, second law, we get that this must be the sum of the voltages, okay, in that circuit as it goes around, as the current's going around. How that then becomes a second order differential equation is the charge is related to the current such that the charge is its derivative, okay? So when we know that that's the case, we can then plug in, so di, if you take the derivative, would get the second derivative. I, you take the derivative, and then q just stays the same. All right, let's go ahead and look at what this means. So what this means then is you have the auxiliary equation, Lm squared plus Rm plus 1 over C. And if you think about the discriminant of that, so b squared minus 4ac, if that's positive, two real solutions for this, okay? If it's critically damped, then it's just equal to 0. So you would just have one solution there, a repeated solution. And then if it's underdamped, then you are going to have complex solutions, okay? So if E is 0 and R of 0, then we would say the circuit is underdamped, okay? So if R is 0 and E of t is 0, then we're going to end up with this situation right here where you'll have negative 4 over LC. And so in that, I think that should actually say underdamped, not undamped, but underdamped situation, you end up having a simple harmonic, which would make sense because that square root on the inside, you have the negative, you'd have a sine cosine piece. And so the electronic vibrations don't go to 0, they just stay in that simple harmonic form like a sine or cosine function. All right, so let's look at an example here. Find the charge on the capacitor in an LRC series circuit where you have L, R, and C. E of t is 0. And then we have some initial current that's going through, okay? And I of 0, it says, is also 0. So let's plug this in. Now remember, it's L, second derivative of Q, plus R, first derivative, 1 over CQ, and we're going to say this is equal to 0. Okay, because that's our E of t. So let's write 0.25 as 1/4. I'm going to write this as Q double prime. That's a little bit easier to write there. 10Q. And then 1 over, ooh, what's that? Okay, tenths, hundredths, thousandths. So 1 over 1/1000th would be 1,000. Sorry, that should be Q prime. Okay, now the easy thing to do is actually just multiply this through by 4. So let's do that. And so I need two numbers that multiply to 4,000 and add to 40. I don't think that there are going to be anything, right? So m equals negative b plus or minus the square root of b squared. Let me just double check. Should be 1,600, right? Yes, 1,600 minus 4 times a times c all over 2a. Okay, so inside here, I end up getting 14,400. Let's take the square root of that. It's 120. So I get negative 20 plus or minus 60i. Therefore, our equation for Q is, let's write a C1 in front of that. C1 e to the negative 20t cosine 60t plus C2 e to the negative 20t sine of 60t. Now, in the problem we talked about before where it would just oscillate back and forth completely, remember R was 0 in that case. R is not 0 in this case. R is 40 in this case. And so this is going to end up going down to, if you look at a graph of this, with that negative exponential power, this is going to end up kind of like fizzling out over time. Okay, kind of like that. All right, let's look at our initial conditions on here. So it told us at the beginning that Q of 0 was Q naught and I of 0 was 0. Now remember the relationship between I and Q. I is Q prime. Okay. So when I plug in 0, my e's become e to the 0 is 1. Cosine of 0 is 1, so that's going to stay. So I get Q naught C1, but my sign goes away. So C1 must be Q naught. If I take the derivative, okay, and then plug in, let's see what I get. Okay, derivative of the first times the second plus the first. Now, when I take the derivative of the second and I plug in 0, 0, right, I get a sine function. So I'm just going to write that because I know that's going to be 0. Okay, same thing when I take derivative of the first times the second, I get a sine piece here, so I'm not going to worry about that. But then plus the first times the derivative of the second, I would get 60 C2 e to the negative 20t cosine 60t. And so I know that 0 must be equal to negative 20 Q naught plus 60 C2. If I add 20 and divide by 60, I get that C2 must be 1/3 Q naught. Okay, and so I'm going to just go ahead and replace that in my equation part right here. And that's going to be my final answer.